Hi, everyone. I'm Xander Kelly, and this talk will be about my work on de-randomizing the switching lemma. First, let me just get some definitions out of the way. So a DNF of width W is just some Boolean function on n bits, and it's of this form. It's an OR of some terms, and each of these terms are an AND of some W literals. So a CNF is just a function that's a negation of a DNF. For this talk, we're going to talk about techniques that are sort of ambivalent to taking negations. So without loss of generality, we can just go ahead and focus on DNFs for simplicity. Now, more generally, we're also interested in the computational model of constant depth circuits. So I won't be too specific about the exact details of that that define that function class, but here's a typical example. This is a circuit of depth 5, I guess, if this A is still an AND of some literals. And so the important complexity parameters to keep track of for constant depth circuits is their size and their depth, size M and the depth D. Okay, so Hofstad's switching lemma. So Hofstad's switching lemma is an important tool used for analyzing low-depth Boolean circuits. So what does it say? It says that if you have a function which is a DNF or a CNF with terms or clauses that have bounded width at most W, then what are we going to do to this function? What we're going to do is randomly set most of the inputs. We're going to leave about a 1 over W fraction of the inputs free. And what happens is that with high probability, the resulting function on the remaining bits that have yet to be set can be represented as a low-depth decision tree. So the reason for the name of the switching lemma is that since a decision tree of depth D can be expressed either as a width D DNF or a width D CNF, you can use random restrictions to switch one into the other. And so using this fact, you can argue that iteratively applying a bunch of random restrictions to a constant depth circuit will likely cause the entire circuit to collapse to a small depth decision tree. So ultimately, this demonstrates a weakness of the computational model, and that weakness can be used to prove lower bounds. Okay, before we move on, I need to just introduce some notation for restrictions and selections. So a restriction, you can just represent it as a string with n coordinates. Each symbol is either a 0, 1, or a star. Intuitively, this corresponds to a partial n-bit assignment. So the stars are signifying locations where we have yet to decide how to set those coordinates. And then in the locations that are not stars, we've gone ahead and assigned those inputs either 0 or 1. And then two restrictions can be composed coordinate-wise in the natural way. Essentially, you take your first restriction, look at all the locations where it has stars, and you set those locations using your second restriction. And also a Boolean function can be, from a Boolean function, we can define the restricted function in the natural way, where if we want to look at the restricted function's value on X, we go ahead and take X and use it to fill all the locations that have stars in row. Okay, so also often we wish to either mentally or actually when we create the restrictions, separate the process of defining a restriction into two stages. One, where we decide up front where we're going to put all the stars. And then with some separate process, we decide how we're going to assign all the bits that are not stars. Okay, so for this purpose, I have this selection notation here that I need to introduce. And you take some selection vector t, which is determining the locations of all the stars, and some assignment vector y. Okay, and then together you define this restriction. I denote it like this. And the ith coordinate is a star if ti is 1. And in the locations where ti is 0, you go ahead and just fix it to yi. Okay, so now we come to the main topic of the work, which is de-randomizing the switching lemma. So various works that construct objects which are in some way provably pseudorandom with respect to constant depth circuits, ultimately they rely on some kind of de-randomization of the switching lemma. So we have these examples from the literature, a bunch of different pseudorandom objects, which are indistinguishable to constant depth circuits from truly random objects, and they all rely on the de-randomization of the switching lemma in some form. So what do I mean by de-randomization of the switching lemma? Is some explicit construction of a set of restrictions of size as small as possible that nevertheless satisfies the property that if you pick a random restriction from that set, it simplifies DNFs about as well as an actual random restriction would. Okay. So an important distinction here is that some applications require restrictions of the form tau with selection vector t and assignment vector y, where both t and y are generated pseudorandomly. Now, there are other applications which require only the selection vector t to be pseudorandom. So this is the setting which is the focus of my work. And yeah, so in the talk, we'll talk about how to pseudorandomly pick some selection vectors t such that this restriction rho defined by selection vector t picked pseudorandomly and assignment vector u picked truly randomly still satisfies the switching lemma. Okay, so we're about to get to probably the main application, which is constructing pseudorandom generators. So just some definitions and parameters to go over. Pseudorandom generator is an explicit, efficiently computable mapping. So it takes L-bit truly random seeds and it stretches them into N-bit inputs. And these inputs need to be indistinguishable from random inputs to some function class. So sometimes it's more convenient to talk about the corresponding pseudorandom distribution, which is just the uniform distribution over all the outputs of the generator. And we say that the distribution x epsilon pools a function if the function can't tell it apart on average from uniformly random inputs with advantage more than epsilon. Okay. So anyway, the parameters to keep track of are the seed length L, which we want to be as small as possible, and the error epsilon, which we also want to be as small as possible. Okay, so one thing I want to highlight is that the switching lemma is ultimately the power source for all strong unconditional hardness and pseudorandomness results known for the circuit class AC0. So here is a sampling of those kind of results. So one thing is it gives strong correlation bounds for the parity function. And then you can take this average case hard function and plug it into the generic Nissan-Wigderson framework and get a PRG with this seed length. So log m, m is the size of the circuits, to the 2d plus 6, so that's the depth. Now this Nissan-Wigderson framework, it's generic and it can take any average case hard function, but ultimately the only average case hard functions we know, that are very hard at least for constant depth circuits are the hardness is proved using the switching lemma. So ultimately the fact that this generator works, you can trace it back to the switching lemma. And then, okay, so alternatively, something else we can derive from the switching lemma is some Fourier analytic bounds on the properties of constant depth circuits. And you can use these Fourier analytic bounds to show that AC0 functions are actually fooled simply just by k-wise independence, where k is like log m to the O of d. And then another thing you could do to get a pseudorandom generator using these Fourier analytic bounds is use the flexible polarizing walk framework. And so in any case, all of these guys ultimately can attribute their success to the switching lemma. And the current best pseudorandom generators for constant depth circuits, which get the seed length all the way down to log m to the d plus a constant, originate from the work of Trevisan and Shui, and their pseudorandom construction relies on the switching lemma in the most direct way so far. It's actually just built directly out of iterated pseudorandom restrictions. So Trevisan and Shui show how to construct pseudorandom restrictions. In fact, they get pseudorandom t, selection vector t, and assignment y, and they use about log m cubed truly random bits to be able to sample those restrictions. Okay, so these restrictions are the building block of their construction. However, by some hybrid argument magic, there's some truly random vector u that appears during the analysis. And it turns out that for this application, to show that their construction works, that it successfully fools constant depth circuits, it's only important to be able to generate selection vectors. So that's one of those applications I was talking about where we just need to generate selection vectors pseudorandomly, and we can allow the assignment to still be truly random. Okay, so our main result is that in this setting, show how to generate selection vectors t satisfying the switching lemma using only log n random bits. And this, I don't list the dependence on the error here, but that's also, log 1 over epsilon, about as good as you'd like. And in total, the whole thing, besides the log factors, is about as good as you would hope for this problem of generating just the selection vectors. In fact, we show that any pseudorandom distribution over selection vectors t, so long as it satisfies some fairly mild and generic pseudorandomness property, is sufficient for the switching lemma. So what is this pseudorandomness property? It's this property we call here k-wise p-bounded, and the requirement is that for every small set S of size at most k, you look at the coordinates in S and ask what is the probability that ti is equal to 1 on all those coordinates simultaneously, and the requirement is that that probability is at most p to the s. And so you should compare this to the truly random case where we have, say, a product distribution generating t with ti equals 1 with probability p in every coordinate independently. So in that case, we have equality here for every set S, and here we're just asking that for a small set S, we have inequality. And okay, so the good news is you can use standard tools from pseudorandomness, for example, small bias spaces, to generate selection vectors t that satisfy this k-wise p-boundedness requirement, while simultaneously still having a reasonable number of ones, say, omega of pn. Of course, that's something you want, like for the applications in the switching lemma, we want to leave as many variables unset as possible. It's sort of trivial to satisfy the switching lemma if you have no stars at all, but then that kind of derandomization of the switching lemma is not useful. So anyway, the point is that we can easily generate pseudorandom vectors t with this pretty mild property that also has a lot of ones. So we're also having a reasonable number of stars in our restrictions. So down here is what you could say is the main theorem of the paper. So we're asking that t is w plus d-wise p-bounded. And again, we have u is uniformly random in 0, 1 to the n. And we have this requirement that p is about 1 over w. And if all that is the case, then for any DNF of width w, this restriction defined by our pseudorandom selection vector t and truly random assignment u satisfies the switching lemma in this sense. We get this probability bound that the decision tree depth of the restricted function being larger than d is at most this quantity. So now let's return to this application we discussed earlier, which was constructing pseudorandom generators for constant depth circuits. Specifically, we're focusing on the best construction so far due to Trevisan and Schwade. That's built out of iterated pseudorandom restrictions. And originally in their paper, they showed that this construction obtains a seed length with d+3 factors in log of m over epsilon. Then subsequently, Avishai et al. Gave an improved analysis of a small modification of this construction, showed that you could actually get d+1 factors of log of m over epsilon. Now finally, plugging in our improved derandomization of the switching lemma, due to this work, we can actually get just d factors of log of m over epsilon, ignoring some log factors. And the story I want to tell about this is sort of like an analogy to hardness versus randomness. So in the hardness versus randomness setting, you start by assumption with some average case hard function. You put it into some machine, and at the other end, you get a pseudorandom generator. Now, the quality of your pseudorandom generator you get, of course, depends on the quality of the average case hard function you started with, but then also on your reduction, like how much hardness did you lose along the way? How much overhead does your reduction have? How much are you wasting the hardness of the function that you started with? And a natural goal is to try to get, a hardness versus randomness reduction with as little overhead as possible, really just squeezing all the hardness out of the original hard function that you had as possible. So the reason I'm saying that's analogous to this situation is, as we discussed, all the known pseudorandom generators for constant depth circuits, they rely, maybe in a roundabout way, ultimately on the switching lemma. So what I'm saying here is a natural goal is to really try to get the absolute best seed length that you could possibly get out of the switching lemma, squeezing every last drop out of it possible. And the claim here is that we're really, really closing in on doing just that, because, so the reason I say that is, if you were able to obtain a further improved seed length, just slightly improving the dependence on m over epsilon, this would imply new circuit lower bounds. It'd be a breakthrough result in circuit complexity. In particular, you really don't expect to do it just from the, taking the switching lemma, putting it in a box, and then you get something out which is better than the switching lemma. It's in that case, it's likely that really the thing doing all the work is inside your box. So that's the story here, that we are really getting basically the best pseudorandom generator you can get. Now, that's in terms of factors of log of m over epsilon. So I want to be careful not to oversell this too much. I mean, there are some other directions you could still improve the seed length in. So for example, certainly we'd like to get rid of this log n factor. No reason why we shouldn't be able to do that. And then in another direction, for example, there's a paper by Cervedio and Tan where they get a better dependence on the error epsilon than we get here. So they only have a single factor of log of 1 over epsilon. The number of total factors in both log m and log of 1 over epsilon is worse, but they do get just a single factor of log of 1 over epsilon. And so something you could try to get, it would be like the best looking thing based on the switching lemma, I think that you could feasibly get, is a seed length of log of m to the d-1, so d-1 factors of log of m, and a single factor of log of 1 over epsilon. So certainly you could strive for that without proving any new circuit lower bounds. Okay, so thank you so much for listening. I really appreciate it. And if you have any questions or comments, I would really look forward to talking to you about them at the poster session. Thanks.